This is Team 4's solution for the Deep Visual Navigation Final Challenge of the Robotics, Science and Systems course in spring 2018. Throughout the course, we implemented robotic planning and control algorithms, given a LiDAR capable of accurately determining distances to obstacles. However, LiDARs are expensive and heavy. Developing accurate navigation methods based solely on camera images would enable cheaper and lighter robots. The objective of this final challenge was to train a deep neural network capable of autonomously driving a robot using only camera images. Our approach consisted of three main components: labeling data, designing and training network architecture, and implementing control on the robot. Labeling data consisted of labeling processed ROSBAG images with values of collision or no collision for a set of given robot actions. Once trained, the network output collision probabilities for any given image. The robot then largely chose actions that minimized collision probabilities.
The training data was constructed from a set of ROSBAG images and corresponding LiDAR scans collected in the same environment the robot was tested in. Images were depopulated, downscaled, and grayscaled for faster processing. Robot angles were discretized into a set of 25 turn angles, evenly spanning the range from -35 to 35 degrees. Trajectories for each turn angle were calculated based on the Ackermann steering model, using a fixed speed and look-ahead distance along the trajectory. LiDAR scans were used to determine the minimum distance between the robot's calculated trajectories and any obstacle in the environment, and each action was labeled as in collision or not in collision. This resulted in 25 labeled actions per image.
The network consisted of an input layer, 3 fully connected layers, and an output logits layer. The input layer had 3,600 units. Each unit corresponded to a pixel in the input images, which were downsized similarly as in the training data. The hidden layers had 300 units each, and the output layer had 25 units, corresponding to the robot's 25 possible actions. ReLU activation functions were used for each of the intermediate layers, and the output layer used a sigmoid activation function.
95% of the labeled data was randomly selected as the training set, and the rest was allocated to the validation set. The training set was split into batches of 5,000 images, and the network was trained with each batch for every training epoch. Training was performed using stochastic gradient descent with a learning rate of 0.1 and momentum of 0.9 for around 150 epochs until validation loss stopped decreasing, indicating overfitting. Accuracy on the validation set was evaluated after each epoch. The final value recorded for the network was 93%. L2 loss on the validation set was also evaluated after each epoch. The final value recorded was 0.11. The trained network output predictions of collision probabilities for each possible steering angle given images from real-time camera input. The robot then chose the steering angle deemed least likely to incur collisions, with angles near zero, indicating straight driving, bias to be more likely to be chosen than more extreme angles. This resulted in the robot generally choosing more straight trajectories.
Using the actions chosen by this neural network, the robot maintained an average distance of 0.8 meters away from walls and a minimum distance of 0.2 meters from walls, safe distances considering a robot width of 0.15 meters, and it was able to run in environments similar to its training data, given arbitrary starting angles and positions.